Hello my friends and welcome back to Sky Creative Channel. Today, we're taking you inside the facilities of some of the world's most advanced machining operations. From massive marine engine crankshafts to precision gear cutting, these are engineering marvels pushing the boundaries of what's possible in modern manufacturing. Let's get started. What you're looking at weighs more than 3 average cars combined, over 10 tons of solid steel that needs to be machined to tolerances measured in microns. That's precision so fine, it's smaller than the width of a human hair. Here at Hanshin Diesel, we're witnessing something truly extraordinary, the machining of a marine engine crankshaft that will power massive cargo vessels across the world's oceans. This isn't your typical machining job, folks. NTHE Beast handling this operation is a custom-built horizontal machining center, specifically designed for these colossal components. Look at that massive spindle. It's generating incredible torque while maintaining surgical precision. The machine's bed is reinforced with specialized vibration dampening technology because when you're working at micron-level tolerances, even the slightest vibration can ruin hours of work. And watch as the cutting tool glides across the surface, removing material with mathematical precision. Those cutting inserts are made from advanced carbide composites, designed to maintain their edge even under the extreme forces generated when cutting hardened marine-grade steel. The coolant system is pumping hundreds of gallons per minute, not just for cooling, but to flush away chips and maintain that mirror-like finish. NTHE really impressive part. Every dimension is monitored in real time by laser measurement systems. The computer is constantly adjusting tool paths, compensating for tool wear, and ensuring that massive crankshaft journals are perfectly round and positioned to tolerances of just 5 microns. That's precision manufacturing at its absolute finest. NTHE final inspection involves coordinate measuring machines that map every surface to create a digital twin of the finished product. When this crankshaft finally makes its way into a marine engine, it'll be spinning at hundreds of RPM, generating thousands of horsepower and lasting for decades. All thanks to this incredible precision machining process. Meet the VDF 450-4 TCM, a horizontal turn mill center that's about to show us how German engineering approaches the art of crankshaft manufacturing. This machine is like a Swiss Army knife on steroids, combining turning, milling, and drilling operations in one incredible setup. What makes the VDF Boehringer system absolutely revolutionary is its horizontal orientation and multiple spindle configuration. Unlike traditional vertical lathes, this horizontal setup allows for optimal chip evacuation and gives operators unprecedented access to the workpiece. Look at that turret system. It's not just one cutting position, but multiple tool stations that can engage simultaneously. The machine is equipped with live tooling, meaning those milling cutters can rotate independently while the main spindle turns the crankshaft. It's like watching a perfectly choreographed dance of cutting tools. NTHE heart of this operation is the advanced CNC control system. It's not just following pre-programmed paths. It's actively monitoring cutting forces, adjusting speeds and feeds in real time, and even predicting tool wear before it affects part quality. The machine's thermal compensation system adjusts for temperature variations throughout the day, because even a few degrees of thermal growth could throw off those critical tolerances. And watch as the machine seamlessly transitions from rough turning to finished milling of the crankpin journals. Those journal surfaces need to be perfectly smooth and precisely sized. They'll be supporting connecting rod bearings under tremendous loads. The surface finish we're achieving here is measured in micro-inches, smoother than what you'd find on most optical components. NTHE integrated measuring system is constantly checking dimensions during the cutting process. If any measurement falls outside tolerance, the machine automatically adjusts the next tool path to compensate. It's adaptive manufacturing at its most sophisticated level. NTHE beauty of the VDF system is its complete automation. From raw forging to finished crankshaft, this machine handles every operation with minimal human intervention. Quality is consistent, cycle times are optimized, and the end result is a crankshaft that meets the demanding specifications of modern high-performance engines. This is how precision manufacturing scales to meet global demand. Forget everything you think you know about wheel manufacturing. What you're about to see is how NewTek creates some of the world's strongest, lightest wheels using a three-piece forged construction that's more art than science. NNTHE magic starts with aerospace-grade aluminum billets heated to precise temperatures in computer-controlled furnaces. Each piece, the center, the inner rim, and the outer rim, is forged separately using massive hydraulic presses generating thousands of tons of force. Watch that forging press in action. It's not just crushing metal, it's flowing the aluminum's grain structure to follow the wheel's stress patterns. This creates strength characteristics that are impossible to achieve with traditional casting methods. The forged aluminum is actually stronger than many steel alloys, but weighs significantly less. And after forging, each component moves to CNC machining centers, where every surface is precisely machined. Those bolt holes aren't just drilled, they're gun-drilled and reamed to aerospace tolerances. The mounting surfaces are fly-cut to ensure perfect flatness, and every radius is carefully profiled for optimal stress distribution. NTHE assembly process is equally impressive. The three pieces are joined using high-strength titanium or steel bolts, with precise torque specifications that ensure the wheel functions as a single, integrated unit while allowing for thermal expansion under extreme conditions. And welcome to Von Shawen, where we're about to witness the complete life cycle of precision shaft manufacturing, from red-hot steel forgings to finished components ready for power generation and industrial applications. Our journey begins at the forge, where massive steel billets are heated to over 2100 degrees Fahrenheit. The open die forging process uses enormous hydraulic hammers to shape the steel while it's glowing hot. Unlike closed die forging, this process allows the steel to flow naturally, creating optimal grain structure alignment that follows the shaft's stress patterns. Watch as skilled operators manipulate tons of steel with precision that would make a sculptor jealous. Once cooled, the forged blanks move to industrial bandsaws equipped with carbide-tipped blades. These aren't your workshop bandsaws. They're precision machines capable of cutting through hardened steel while maintaining dimensional accuracy. Each cut is monitored by laser measuring systems to ensure proper length tolerances. NNTHE tempering process is where metallurgical science meets manufacturing precision. These shafts are heated to specific temperatures in computer-controlled furnaces, then carefully cooled to achieve the perfect balance of hardness and toughness. The in-house laboratory performs rigorous testing. Those notched bar impact tests reveal how the material will behave under shock loads, while tensile tests verify the steel's strength characteristics. Every batch is traceable, every result documented. Now comes the precision work. The pre-turning operation removes forging scale and establishes basic dimensions on massive CNC lathes. Watch those cutting tools. They're removing material at rates that would seem impossible, yet maintaining tolerances measured in thousandths of an inch. NTHE milling operations are particularly impressive. These aren't simple cuts. They're complex 3D profiles that must mate perfectly with gear assemblies or coupling systems. The CNC programming for these operations involves thousands of lines of code, with toolpaths optimized for both material removal rates and surface finish. End-finish turning and grinding operations take precision to the next level. Those grinding wheels are spinning at thousands of RPM, removing material 1 micron at a time to achieve surface finishes that feel like glass. The machines are equipped with in-process gauging systems that monitor dimensions in real time, automatically compensating for wheel wear and thermal effects. NNTHE drilling operations use gun drills and deep hole boring techniques to create internal passages for lubrication or cooling. These holes must be perfectly straight and positioned with extreme accuracy. Any deviation could cause catastrophic failure in service. Non-destructive testing is the final quality gate. Ultrasonic testing reveals any internal flaws, while magnetic particle testing detects surface cracks invisible to the human eye. Only shafts that pass every test move to final packaging. From forge to finished product, this process represents decades of manufacturing expertise applied to critical power transmission components. This is how precision manufacturing ensures reliability in the world's most demanding applications. What if I told you that complex steel shaft could be completely machined from rough stock to finished part in a single setup, without ever removing it from the machine? That's exactly what the Okuma MACTURN 550 is about to demonstrate. It's not just machining, it's manufacturing magic. NNTHE MACTURN 550 represents the pinnacle of turn mill technology. This isn't just a lathe or just a milling machine. It's a complete machining center that combines both operations with incredible sophistication. The main spindle can hold and rotate the workpiece, while the sub-spindle can pick up parts for backside operations. Meanwhile, the upper and lower turrets are equipped with live tooling that can mill, drill, and tap while the part rotates. Look at that tool magazine. It holds over 100 different cutting tools, each precisely positioned and automatically selected by the machine's tool management system. The machine knows exactly where every tool is, how much life remains on each cutting edge, and when to automatically change tools to maintain optimal cutting conditions. NNTHE real magic happens in the programming phase. Okuma's OSP control system doesn't just execute G-code, it optimizes the entire machining process. The software calculates optimal cutting parameters, minimizes rapid movements, and synchronizes multiple operations to eliminate idle time. And watch as the operator loads the raw steel stock. The machine's automatic measuring system immediately checks the material dimensions and adjusts the program accordingly. If the stock is slightly oversized or undersized, the machine compensates automatically. No manual intervention required. And now the real show begins. The main spindle grips the workpiece and begins rough turning operations, while the lower turret simultaneously machines features on the opposite end. It's like watching two different machines working on the same part at the same time. NTHE coordination between spindles and turrets is absolutely mesmerizing. As the main spindle finishes turning one section, the sub-spindle moves in to support the part, while live tools on the turret begin milling keyways and crossholes. The machine is executing multiple operations simultaneously, with cutting tools sometimes just millimeters apart, yet never interfering with each other. NTHE surface finish being achieved is remarkable. Those turning operations are producing surfaces that typically require grinding. but the machine's thermal stability and vibration control are so good that we're getting grinding quality finishes directly from the turning process. And watch as the machine seamlessly transitions between operations. Threading, grooving, face milling. Each operation flows into the next with no pause, no repositioning, no secondary setups. The part never leaves the machine, so there's no opportunity for dimensional errors to creep in. NTHE drilling operations are particularly impressive. The machine is using high-pressure coolant systems and specialized drill geometries to create perfectly round, straight holes at feed rates that would be impossible on conventional equipment. Throughout the entire process, the machine is monitoring everything. Spindle loads, cutting forces, tool wear, dimensional accuracy. Hundreds of parameters are being tracked in real time. If anything starts to drift out of specification, the machine adjusts automatically. NTHE final inspection is built right into the machining process. Laser measuring systems and touch probes verify critical dimensions while the part is still in the machine. Any dimension that's out of tolerance can be corrected immediately with an additional finishing pass. In just over 20 minutes, this machine has taken a rough steel bar and transformed it into a precision shaft with dozens of features, all machined to tolerances measured in microns. This is single setup manufacturing at its absolute finest: maximum precision, minimum handling, and consistent quality every single time. Gear cutting has been around for centuries, but what you're about to see represents a revolution in manufacturing efficiency. Dry cutting bevel gears eliminates coolants, reduces environmental impact, and actually produces better surface finishes than traditional flood-cooled operations. Traditional gear cutting relies heavily on cutting fluids for cooling and chip evacuation. But advanced cutting tool materials and machine design have made dry cutting not just possible, but preferable for many applications. The key is in the cutting tool geometry and coatings. These carbide inserts feature specialized chip breaker geometries that control chip formation and evacuation without any coolant assistance. The PVD coatings provide thermal barrier properties that allow the cutting edge to operate at higher temperatures while actually extending tool life. NTHE machine spindle is designed for optimal chip evacuation using high-velocity air systems. Instead of coolant washing chips away, precisely directed air streams blow chips clear of the cutting zone while providing some cooling effect. And watch as the cutting tool engages the gear blank. The cutting action is remarkably smooth, with chips forming in tight coils that are immediately evacuated by the air system. The lack of coolant means we can see exactly what's happening at the cutting edge, something that's impossible with flood cooling. NTHE surface finish being achieved is actually superior to wet cutting in many cases. Without coolant washing away the natural work-hardened layer, the gear teeth develop beneficial compressive stresses that improve fatigue resistance. The cutting parameters are precisely controlled, speeds and feeds optimized for the specific material and tool combination. NTHE machine's thermal management system is crucial here. While we're not using coolant on the cutting tools, the machine structure itself is temperature controlled to maintain dimensional stability. The spindle bearings are precision cooled, and the machine bed has thermal compensation systems that adjust for temperature variations. NTHE advantages of dry cutting extend far beyond environmental benefits. Tool changes are faster and cleaner, there's no coolant contamination to worry about, and the work environment is significantly improved for operators. Part handling is easier since there's no slippery coolant residue to clean off. NTHE gear quality is exceptional. Tooth spacing accuracy, profile consistency, and surface finish all meet or exceed specifications that would require secondary finishing operations with traditional cutting methods. Yen this is manufacturing's future. Processes that are simultaneously more efficient, more environmentally responsible, and produce higher quality results. Dry cutting represents the perfect marriage of advanced materials, science, and precision manufacturing technology.